Yeah, a very warm welcome here at the joint press conference of DLR, Airbus, Neste and Rolls-Royce about the results of the ECLIF3 campaign. And you have seen already these impressive pictures, and we will have impressive results today. And for this, I'm very happy to have here from DLR the divisional board member of aeronautics, Markus Fischer. And beside Mark Bentel, head of technology and research at Airbus. And then we have Anne Sonneveld. She is SAF technologies and OEM development and relationship at Neste. And then we have Alan Newby from Rolls-Royce with us. He's head of technology and research at Rolls-Royce there. And finally, Christiane Vogt from our Institute of Atmospheric Research. She's there head of cloud physics. So and now we will have short statements by the partners and then presentation of Christiane about the results. So please, Markus Fischer.
Hello everyone, ladies and gentlemen, dear colleagues, dear very warm welcome project partners. Welcome to the DLR booth. Here we show here a number of DLR research and technology activities for climate compatible aviation. And of course you are very welcome to have a visit here. But one of our most critical research topics we are looking at, and in particular today, is towards climate-compatible aviation, are the non-carbon dioxide effects of aviation. Worldwide studies show that the impact on aviation on Earth's climate from non-carbon dioxide effects can be as of importance as the impact from carbon dioxide alone. Contrail cirrus clouds are an important factor here. We wanted to find out how to reduce the warming effects of contrail cirrus clouds, or even better, to avoid them altogether. One method is, of course, to use climate-optimized flight routes, and another method is to use sustainable or short SAF fuels, also known as SAFs. Since 2015 already, when we started the ECLIF1 campaign, DLR has been conducting with partners extensive flight tests to characterize emissions from synthetic fuels. In 2018 then, these flight tests were continuous with the ECLIF2 campaign in Germany in collaboration with NASA, using at that time a 50-50 blend of kerosene and SAF. In 2021, the ECLIF3 campaign started, which we are discussing today, continuing the scientific story and the very first emission measurements using 100% SAF on an A350 airliner aircraft. So using 100% SAF has taken our flight research activities to a new level. And thanks to the extraordinary ECLIF3 campaign, the partners, and we have gained really a vital industrial partnership with Airbus, with Neste, with Rolls-Royce, and a very big thanks also to Christiane, the whole team from atmospheric flight physics at DLR. Christiane and her colleagues were on board the Falcon research aircraft, which you have just seen here as a chaser aircraft in this short movie, that followed the A350 sometimes just from a distance of a length scale of the A350, roughly 100 meter. Really, you call it near field, near field approach. Measuring its emissions, but really feel the turbulence behind such an aircraft. You have seen the view from the cockpit. It is always impressive seeing then the Falcon research aircraft fly so closely behind such a big airliner. And it was truly a great performance from our test pilots and scientists sitting in the Falcon. And of course, of the crew on the A350 and on the crew for the XWB engines and for the delivery of the sustainable aviation fuel. So with ECLIF3 we have developed a vital teamwork which we will continue, and a great partnership between industry and science to pave the way forward for climate compatible aviation. Again, we are very happy to have you here all to show off this remarkable partnership and of course the important results. And with this I would like to hand over to Mark. Many thanks. Yes.
Hello everybody, and thank you, and it's an absolute delight to be here, and it's a real delight to be part of the ECLIF3 campaign, and we're super happy to have been part of that. So I'd just like to give maybe just a few little details about the flight campaign that we did. So first of all, we start with the aircraft. Why did we pick the 350? So one of the features of the 350 is we have three completely separate fuel tanks, the left wing, the right wing, and the center tank, which means we can store three completely separate fuels on that aircraft. So during the campaign, we could have jet A1, we could have HEFA, and we could have a blend in the aircraft at any one time, and within about a 5-minute switch over time, we could have flushed the system and be emitting with the other fuels. So that's a good choice for the aircraft. Then, what did we do? So we ran about 9 flights, and we did 4 ground tests as well. And each of those flights, we took off from Toulouse with the 350, we took off from Munich with the Falcon 20, and then we met together over either the Atlantic, I believe, or over the Mediterranean, where then we could do the monitoring. You heard about the near field, 100 meters, that's pretty close. And then the far field, where about 15 nautical miles, so about 28 kilometers behind, which is when you can start to measure the contrail effects. Within about a 4-hour flight for both aircraft, there's about 1.5 hours of time that you get together. And then from that, of all of those 9 flights, certainly we managed to get good data, and I hope Cristiano will go into some of the details on the data that we got from the near field. Only 1 flight could we get the far field for the contrail measurement. So this is really shows you've got to be in the right conditions, in the right environment to do that. So all of that led to the results of the experiment, and now I'd like to hand over so that we can talk a little bit about the fuels and what was on board. Alicia.
Thank you. I am Astrid Sonneveld. I work with Neste, and in the context of ECLIF3, we were the ones supplying the fuel on board for the research and on board the flight test campaign. So that's why I'm here today, to explain more about the fuel used. Maybe to explain first, as Neste, we are the leading SAF producer. This year, 2024, we're producing 1.5 million tons globally, and we're supplying that sustainable aviation fuel. So it's available here and now, and it's being used. And if we supply to our airline customers, and that's an important remark to make in the context of ECLIF3, we supply our SAF blended. So our SAF is blended up to 50% with conventional fossil jet fuel before use in a commercial aircraft. That's what makes the ECLIF3 campaign different. The aircraft was powered by 100% SAF, so unblended SAF. And if we look in more detail what that fuel was, it's our SAF that is a so-called HEFA SPK, where HEFA refers to the feedstock being used and the technology being deployed to produce that SAF, and SPK refers to the fuel composition and the properties. And to understand the climate benefits of SAF, you need to understand both aspects. If you're familiar with SAF, you may know that SAF, at least our Neste SAF, can reduce the life cycle greenhouse gas emissions by up to 80%. And that is due to the difference in feedstock, so because it's made from renewable raw materials. If we then look to the fuel composition side, then what you will see is that a HEFA SPK is free from aromatics, the ring-shaped molecules that are typically present in a conventional aviation fuel. And because of that, fewer or less aromatics means fewer soot particles emitted, and fewer soot particles emitted is one thing, but it also means fewer ice crystals in the contrails. And I'll hand over later to Christian to present more of the results. But in short, to summarize, SAF is not only benefiting the climate because it's made from renewable raw materials, but it's also helping that it burns more clean, produces less soot, and hence help reduce the non-CO2 emissions of flying. So maybe to finalize with why, from our Neste perspective, this ECLIF3 campaign was highly valuable. I'd say, first of all, because we need to build up scientific evidence. In the context of contrails, we talk a lot about uncertainties. So as an industry, we need to step up and do the research to remove the uncertainty levels. And this is, I think, a perfect example of, having a proper research setup to validate and confirm expectations, because the expectations was indeed that 100% SAF would reduce non-CO2 emissions, but ultimately you need to measure that and you need to prove that, and that's exactly what we've done with this campaign. And I think the second reason I'd say is this was an aircraft taking off with 100% SAF. Not all aircraft today are capable of flying on 100% SAF. So for us as Neste, it's incredibly valuable to work with parties like Airbus, DLR, Rolls-Royce to jointly learn about what it will take to make all aircraft capable of flying on 100% SAF. And on that note, I'm going to hand over to you.
Thank you very much. And like Mark, I'd like to start by saying that it's a great part, it's a great pleasure and a great honor to be part of this team which is delivering such groundbreaking research. I think from our point of view, last year we proved the compatibility of all our in-production engines on 100% SAF. And indeed, we carried out the first transatlantic crossing on a SAF-fueled aircraft. And indeed, it went across the Atlantic on SAF and returned on normal fuel, completely unmodified engine. And I think that's what we did here as well. This wasn't a special engine that we put in service. This was a standard XWB 84K engine. And I think what this test proved is that not only that sustainable aviation fuels can give a significant contribution to CO2 reduction, but this test has proven also that such fuels can give a significant effects on the reduction of non-CO2 effects, and I think that's what we're going to hear more about now. But from our point of view, I'll keep it relatively short. From an engine point of view, it's relatively uncontroversial. We put it in, it burned it, and it ran really, really well, and we've proved that we can operate on 100% SAF. So with that, I'm handing over to Christine.
So now you get the perspective from an insider from the aircraft campaign who was sitting in the aircraft, feeling all these turbulences from the near-field measurements, also from the far-field measurements. That's really exciting. So in those near-field measurements, it's really like going on a gravel ground road, and the aircraft is pushed back. We pull full thrust. The aircraft is pushed back. We get in and out of the emissions, measure the emissions, measure background, and from that get our results and calculate the climate impact. For the far-field measurements in the contrails, it's completely different. It's like surfing on the wake vortices, on those contrail wakes and vortices, and getting the emission measurements in the far field in, as the colleague said, 20 to 40 kilometers distance, to then probe the contrails in an unperturbed way. So how did we do these measurements? And the colleagues already highlighted the new points of these emission measurements. So that is that we had a large aircraft that were the first emission measurements behind the A350. I think it was the first produced aircraft by Airbus, first Airbus aircraft. So the flight lab, which was used here for these emission measurements with these Rolls-Royce engines, and the first time flying with the 100% sustainable aviation fuels, and with our small Falcon chasing the A350 aircraft and making the measurements. how do we do these measurements? So how do we really measure the contrail properties? We measure the contrail properties with the cloud probes, which are on the wings of the aircraft, in order to get the undisturbed particle measurements. We measure the trace gases, the NOx, the CO2. With the trace gas inlets, the air is sucked into the aircraft, and then we use our instrumentation to really detect the NOx emission indices, the CO2 emission indices, and we have a meteorological nose boom to also measure the turbulence in this aircraft, and that also helps us to keep this aircraft still, while flying in these very turbulent conditions, keeping it safe. Yeah, here you see a photo, a cockpit view from our Falcon when we try to get into the emissions here, into the contrails. We get in and out in order to probe both the trace gases, the particles, and the contrail ice crystals, and then to get to our results here. And that is shown here, actually. What you see here is the number of soot particles that are emitted per kilogram of fuel versus the number of ice crystals and contrails that we detect. And for the Jet A1, so for the conventional fossil fuel, we have about 10 to the 15 soot particles and about the same number of ice particles which get activated. So each of those soot particles leads to an ice crystal and contrails. But for this 100% HEFA SPK, we see a strong reduction in soot particles and related a strong reduction in the ice crystal number in contrails, as expected. But how is this now related to the fuel composition? And Neste, you already announced this. So what is the driving motor? Why are those soot particles reduced? And it's really the aromatic content of the fuel. The aromatic hydrocarbon rings, they are the precursor, very good soot precursors. And what we could show here, that for a very low, near zero aromatic HEFA, 100% HEFA SPK, the number of ice crystals, of soot particles, and of ice crystals was significantly reduced. And so we could really prove this chain with those measurements from the fuel composition, aromatics and hydrogen content of the fuel, leading to the soot particle emission, leading to ice crystals. For SAF, this is reduced, and now we have to calculate the climate impact. What is the impact on the climate for those contrails? That is what you see here. That's global model simulation for the fleet in 2018 with Jet A1, with conventional kerosene. And you see the high climate impact region in those heavily flown regions. In total, aviation contributes with about 72 milliwatts per square meter, so almost as much as the carbon dioxide emissions from aviation to the warming from aviation. And that is now the reduction that we get when using this 100% HEFA SPK. So there's a significant reduction, in particular in those regions where the contrails form and where they are most climatically relevant, active. So we could, with these measurements, really prove that SAF does have a double benefit for climate, lowering the CO2 footprint, but also lowering the particle emissions and the contrail climate impact for allowing to short-term reduction measures. And I think that is really a highlight that has been achieved with this international collaboration that could only be achieved in collaboration with industry, with Airbus, with Rolls-Royce, with Neste. We couldn't have got the results, one of the partners alone. I think it was a very a highlight project also for DLR to do those measurements, which are published now in the Merkel et al. In ACP. Thank you.
Yeah, thank you very much, Christiane. Very impressive. I think everyone can imagine a little bit more now how it is to sit in such an aircraft, flying so close behind an A350. And yes, now we would have some more minutes for some questions. So, are there any questions now? Or,
if not, I might add one point, because if we go to our last slide, if that is still possible. Because here you have the clear documentation, also the visible documentation. The Airbus aircraft with a Rolls-Royce engine with 100% did not produce a contrail, while our Falcon using Jet A1 and an old engine did produce a contrail. So very convincing.
Okay, that's great. Okay, good. So last chance, if there are any questions in the big round. If not, then of course you're very welcome to ask for individual interviews. Just come to me and then we will arrange everything you need. And as well, you're very welcome then afterwards to visit the DLR booth. And if you have there any questions, yes, also come to me, to my colleagues, and we will answer you any question you have. Then thank you very much, and thank you very much here on the stage. Thank you.